Is enthalpy heat?
No.
Okay, how are they related then?
Heat is only when it's leaving. Or going into something. It's a transfer of thermal energy.
Okay, but there's no relationship between enthalpy and heat transfer?
Well, heat transfer is part of that.
Enthalpy and heat transfer are the same under one condition. What is it? Yes. Okay? Now we talked about calorimeters and using really the idea that energy in is the same energy that we get out. If that makes sense. If I get energy in, it had to come from the out. If that makes sense at all. Really? Does that make sense at all? Okay? Exothermic energy, or the energy leaving somewhere, came from somewhere. Endothermic energy, the energy that got taken in, had to come from somewhere. And it's always the same amount, just different direction, if you will. And so, you can use calorimeters really nicely because you can do a lot of reactions in water, and you can weigh the mass of water, we know the specific heat of water, you can calculate the change in temperature when you put an object in water. Whether the water's temperature goes down or goes up, you can figure out what that change in temperature is. Okay? So, let's do this problem. I think you're going to find a lot of calorimeter stuff is really a solution chemistry. So what you have is, a lot of times a couple solutions are mixed, and in those solutions you have particles that can interact with each other and form a chemical reaction, and obviously within the process of a chemical reaction there's energy changes, right? Okay? Just the changing of the bonds is going to change the potential energy, and there's going to be a lot of energy converted either one way or the other. So, here we got another, looks like calorimetry mixture solution problem. Looks like very similar to the previous one we did. I would say it's probably almost identical. Because it looks like they gave us two solutions, they gave us temperature change, they gave us density. So, now I could take this and this and write two separate equations. Would just be those guys breaking up into their ions, correct? You guys remember when we did solution chemistry? We mixed two things together and we tried to identify what the precipitate was, how much of that precipitate will form, things like that. Okay? That's essentially what this is, except for we're not trying to figure out how much precipitate is forming, we're trying to understand the energy transfers between that process. Make sense? So here we got these two guys. First off, nitrate is one of those guys that does dissolve almost every single time. Remember the solubility rules? I know you don't, because you didn't do very well on that part of the test. Okay? So this is not going to react with sodium, but barium and sulfate can react and it produces our solid precipitate. Great, we've got a reaction going on here. There's probably going to be some energy transfers and some changes in energy. Okay, so some things we know. Change in temperature. I already got that down, huh? Okay. So it'll just be your final minus initial. We know specific heat of water. I don't know if I need to write this down. Okay, what does specific heat tell you again?
The amount of joules needed to raise 1 gram 1 degree.
Okay. Why is that useful? What in a big picture, what does that really tell you? Sure, but that becomes practical in how fast something,
how
fast something can heat up, or how slowly something heats up. Okay, because usually when you add energy at a constant rate. Like when you put a pan of water on your stove, you know, you don't have fluctuations of energy you're adding. You know, you're not increasing it and then decreasing it and increasing it. It's usually a pretty standard constant rate. Okay, other things. Got some density. And we're probably somewhere along the line here going to use our specific heat equation. So now, I know I kind of used for the calorimeter the other day, I used a rock example, plopping a rock into water. Well, think of, when you think of solution chemistry, you really got a lot of really small particles in there. So even though we can't see them, they are there, and they are part of the reaction that's occurring. So, if I were to just write the reaction that I'm desiring, what would it be? There's a reaction going on here. What is that? If I wrote the chemical equation for that reaction, what would it be? I just want what's actually reacting.
BA plus SO.
If you remember, things became a lot easier in solution chemistry when we could identify one-to-one ratios, correct? Everything here is a one-to-one ratio. And what's even more vital here, guys, is this. That the things that these come from are one-to-one ratios with their particular molecule. Okay, now notice the nitrate wasn't a one-to-one ratio, but we're not dealing with nitrate, are we? Barium is a one-to-one ratio from its thing it comes from, and a one-to-one ratio with the thing it's reacting with. Sulfate is a one-to-one ratio with the thing it comes from, and a one-to-one ratio with what it's reacting to form. Okay, so thankfully they gave us the one-to-one ratios all the way through. It didn't have us deal with sodium and nitrate. That makes it quite a bit easier, or at least makes our assumptions quite a bit easier. Okay, can we figure out the amount of energy transferred to the water in this case? Or taken from the water? I guess I can assume. Well, I can assume it's transferred to the water. Why? Why can I assume that the chemical reaction is an exothermic one? Why can I assume that?
It's increasing.
It's what?
The temperature increases.
The temperature of what increases?
Water.
The water. Okay, if the temperature of the water decreased, then it'd be endothermic, and the reaction would have had to have taken energy from the water. Well, when you take energy from something, what happens to its temperature? It drops. Okay? So let's figure out the energy transfer here. We got to figure out the mass of water. How do we do that? Does it give it to us? It doesn't give it to us directly, does it?
Yeah.
Yeah, that's it. Alright, this poison ivy, man.
It's 1 gram per mole.
Per milliliter. You have to use your volume.
So it's why did I become mole? 1 milliliter.
So we got actually 2 liters, right? Yep. So 2 liters would be 2,000 milliliters. And 1 gram for every 1 milliliter means I got 2,000 grams. Does that make sense?
A lot of water.
It's actually not as much as you think. I mean, it's 2 liters, so it's a 2 liter. Think of a 2 liter pop bottle. I need to get a shot. We'll get some steroids.
You get
What?
I did that one. Really bad though.
Where do you get poison ivy from?
I just got there, put it there. Got a lot of it.
Where do you,
Mine was
where do
like,
you get
I
poison ivy
hauled
from?
wood.
Part of the greatest decision I ever made, shingling my in-laws' house.
See it from Kalamazoo.
I remember I was picking up shingles off the ground. First of all, they live in a really wooded area. Picking shingles off the ground, I go, that looks like poison ivy right there. Sure enough.
Never gotten poison ivy.
I didn't think I thought I was immune to it because I feel like I've been around it a lot. But, okay, so we got 2,000 grams. we got a CSB, or a specific heat of 4.18, and our change in temperature was 3.9 degrees Celsius. All right, what's Q?
Those numbers together.
Thanks.
Wait, is it 3.1 or
3.1, yep. You get a theoretical Jolly Rancher.
Should go to Daryl and tell him.
3.1? You give it to him.
Say, I proved Mr. Kramer wrong. Can I have a Jolly Rancher from you?
You
Ouch.
need a lot more to calculate than doing.
Well, I tend to like the higher level classes.
Because I remember last year,
That's just
they
reality.
had said that you would just give them to.
All right, what'd you get?
20.
Approximately what, like 2,600 or?
Yeah.
Can I turn that into kilojoules? Is that cool?
It'd be 26,000.
So I changed that to a
Is
negative
it 26,000? Or that, do you have?
26,000, yes.
Okay, that.
So yeah, you move the decimal 3 spots to get kilojoules, right?
Yeah.
I added a negative on that. I know this didn't give us a negative because we're talking about from the water's perspective, you'd be gaining it, but we're really worried about the system's perspective or the chemical reactions perspective, which it should be the opposite, correct? Does everyone understand that concept? That's a very, very important concept to realize, that the water would have gained it in this context because it had an increase in temperature. Well, it had to have received it from the reaction, and we already know that we have to have it from the system standpoint when we're doing these. I want to use more room here, but
Just pick it up. There's so.
watch this won't come off. Guarantee it.
It won't come on here.
Look at it. Pretty close. You can see all the blue. It's like there's like little wrench holes in here.
It is scratched up.
Yeah. Okay. Great. Now what? We figured out the amount of energy that this particular situation got, but this is just total energy. We don't have it per gram or per mole or per anything. It's just this is the amount of energy that got transferred. It wants it how?
Purple.
Per mole. Okay? Now, remember that this is going to be a 1-to-1 ratio. So let me show you how you can do this both ways. Thankfully, they gave us really nice numbers here. 1 liter, 1 mole per liter. So each of these things have how many moles? 1. Okay? Well, 1 mole of the whole thing would equal how many moles of the barium?
1.
Because of the what?
1-to-1 ratio.
I got 1 mole of this. Okay? 1 liter, 1 mole per liter, so 1 mole again.
Yeah.
1 mole of the whole thing means how many moles of sulfate? So thankfully, they gave us equal amounts of both, and it's a 1-to-1 ratio for everything. So it doesn't matter whether I use the barium to figure out how much of my total form, or the sulfate to figure out my total form.
What if they were different? How do you know?
You would have to use the living reactor.
See, that's fine.
Yeah, like if I have 1 mole of this and 2 moles of this, I can only produce 1 mole of this because of the 1-to-1 ratio. I would have an excess of 1 mole of the other thing. I doubt they'll do that, but they could. I don't remember them doing that, but I typically give you hard homework for a reason. All right. So I know based on this that I got 1 mole of this whole thing. So thankfully then I can take that total energy divided by 1 mole, and what do I get? So it's just this divided by 1 mole, and your answer is negative 26 kilojoules per mole. Now, it isn't always going to be a nice 1 mole number. Could they have wanted it in kilojoules per gram? They could have. They just had to convert that moles to grams and then divide by that mass. Does that make sense? Okay.
So you would have found, in this case, if they wanted per gram, you would have figured out the moles of barium sulfide.
Yeah.
And then Muller Mass check. And then flat 126.
Yes.
26, okay.
Yep. Any other questions? Okay, you guys remember what state function is?
Things that are separate from
Yeah.
Yeah, so you don't need the path for state functions. If you remember, enthalpy is a state function because your energy and your pressure and your volume are all state functions. Doesn't matter the path. Okay. And then what we got is a few homework assignments that we can work on now. And again, you can come check your answers. Make sure we're doing this right. I think it's 57 is like a calendar problem.